Welcome to the Sci-Fi Guest Show. I'm your host Jack, and in this podcast I'll be talking to different scientists about their research and the topics they know best. In this episode I'm talking to Andrew Yong about his work in the field of particle physics at the University of Edinburgh, where he's studying for his PhD. So welcome to the show, and to start off with, I'd like to ask what particle physics actually is, and what was it that made you want to study this?
Yeah, sure. So the particle word just refers to particle physics. So this is, if I try to put it in like a one-liner, is the study of the very small and sometimes very fast. But the theory part of it just associates with people who try to come up with a framework to describe the world at the really, really, really small scales. When you mush these two words together, these are the people who study particle physics and try to come up with some model that describes the world, building on like previous works, previous foundations. Why I wanted to become a particle physicist? I don't think there's any profound answer to this. I just thought it was really cool. I mean, it's more like in hindsight, it's quite incredible that we have any chance at all to study things that are beyond our immediate senses. Like, so where we're looking at, looking in inverted commas, we're looking at things that are really small, like things we can never actually see, and in environments that are so extreme that that's not hospitable for us. So it's quite incredible that we still get this opportunity to study and to try and understand, in some sense, a completely different world. The sort of working analogy that I have with people is during the not so serious hours of particle physics, almost like playing with Lego. And there are a lot of different kind of components, like you have the different length of bricks, you have the flatter kind of pieces. So in some sense, you can build this physical world, or at least the ethos is that we can build this physical world with these, we call them fundamental building blocks of nature. Particle physics concerns itself with things at the scale of the atom and smaller. And in my particular group, we focus on the subatomic scales.
What is the subatomic that's interesting for you to study, and is this quite a new field, or is this something that's been going on for a long time?
Yeah, so actually we can dial back to like the early 20th century, where we have Rutherford discovering the constituents of the atom. So, for example, the simplest one is something like hydrogen, which is just made of a proton. But of course, when you get to more and more complicated atoms, a carbon atom, you have multiples of these protons. And when they looked at the sort of like electric charge, they realized that there must be something else in the atoms. So we found that by the early 20th century, that the atoms are made of these smaller parts, if you will, called the protons and the neutrons. Now, it sounds great because all life as we knew it at that time in the 20th century are made of these atoms, right? Things from the periodic table. So the atom consists of these electrons, and they surround this center that consists of protons and neutrons. When we move forward to the mid 20th century, post Second World War, there is this phenomena that is happening. They call it a particle zoo, because people were discovering more and more of these sort of like, they're discovering more and more cousins of the protons and the neutrons. And they couldn't find a way to neatly classify it. It's become a bit of a goal now, this habit that has formed into this goal in particle physics, where we try to classify things using a very small set of rules. It took very brilliant people, some of them like Murray Gell-Mann and many others, theorists in this case. They came up with a theory that perhaps we actually have an even smaller constituents. So smaller pieces that make up the protons, the neutrons, and their cousins. They just gave it an amusing name. They called them quarks.
Is there any reason why they were called quarks?
Yeah, so it came from one of the James Joyce's books that Gell-Mann was reading at that time, and there's this term called the free muster quark within the book, and I think Gell-Mann was reading through this when he came up with the idea. I mean, at this point, these things are so abstract, it's not necessary to try and name them as something relatable, in our everyday life. Yeah, so the idea of these quarks at that time is a pretty abstract and mathematical concept. Physics aims to describe the physical world. So we have to find a way to prove the existence of these quarks. Therein begins this whole set of experiments. We can talk about that later if you want, but it turns out that there are a multitude of these quarks. Each different one of them, we call them flavors. So there are 6 flavors of quarks. Again, this flavor has nothing to do with the taste. So today, we have confirmed 6 different flavors of quarks, and they can be grouped into 3 pairs if you think of the way the name works. So there are the up and down quarks, and they are known as the first generation. There are the charm and strange quarks, so they're just the second set. And then there's the top and bottom quarks, so they form the third set. Now, when we dial back to the 20th century picture about the center of the atom, so you have these protons and these neutrons. The protons have 2 of these up quarks and 1 down quark, whereas the neutron has 1 up quark and 2 down quarks.
So what's the difference between the up and down and different types of quarks?
Yeah, very good question. Yeah, so how do you distinguish them, right? So they form these 2 pairs. Sorry, they form these 3 pairs. And within the pair, they almost have these opposite behaviors. The ones that are called up, charm, and top, they actually have a positive charge, positive electric charge. You see that when we combine them together, they must have the same charge as the protons or the neutrons. So these 3 that I mentioned just now, the up, the charm, and the top, they have a charge of plus 2/3. Now, it's a bit weird, right, to have a fractional electric charge. Normally, if we think back to high school, the proton has a charge +1, and the electron has charge -1, so that they cancel out nicely, right? But these quarks have these very strange fractional charges. The remaining 3, we have the down quark, the strange quark, and the bottom quark. So these have negative -1/3 charge. So once again, that seems a bit odd. But when we think about the protons, so the proton has a positive charge, right? We have a charge of +1. And then, as I said earlier, it's made of these 2 up quarks and 1 down quark. So you can do this this mental math across the radio with me. You have 2 up quarks, so that's 4/3. And then you have 1 down quark, that's -1/3. So you add them up together, and they give you a +1.
Oh, so the fractions are kind of relative to the charge of the thing they make.
Yes. So in some sense, it's this categorization that physicists were doing through the 50s until the early 90s, where they know that these quarks, if they form the constituents of the larger protons and neutrons, they must, in total, add up to the same kind of properties that the protons and neutrons have, for example. So in that sense, the charge has to balance out like that. There are also other properties that separates these 6 different flavors. Mainly, that's their mass. So before I go on to list them out, we have to remember that these quarks, right? They're the most basic Lego blocks.
Do you think in the future there would be a smaller level again that made up those?
With questions like that, I guess the experimentalists and the theorists will have different takes on that. So, of course, from the theoretical point of view, you've heard of these popular science claims as well. There are a lot of ideas out there that are waiting to be explored, waiting to be experimentally explored. So you hear of these things called strings, that come from string theory. In string theory, that's proposed to be the smallest constituents that would eventually make up the quarks and so forth. There are lots of these very, wonderful and sophisticated theories out there, but at the moment, the experiments don't have the technology to probe it, and it's not clear on a case-by-case basis whether we can achieve the technology to actually probe them. So as far as we know, in 2020, the experiments give a very strong suggestion. In fact, it's been confirmed experimentally. These quarks, these 6 flavors do exist.
So how do you experiment with things that are so tiny in order to actually find out anything about them?
In today's sort of experiments, it's become highly sophisticated. But we can start from something simpler. We can think back of the experiment that made Rutherford conclude that the atom is made of this positive center. So remember, transitioning from the 19th century to the 20th century, there are competing models on what the smallest indivisible, quantity of matter is. In the early 20th century, an idea of this periodic table. These tell you how each atom, quote unquote, looks like. So Rutherford set out to do this experiment where he fired, what we call in physics alpha particles. He fired these things called alpha particles. So this is one of the types of radiation that we experience. So the alpha particles are basically this really heavy particle emitted out of a radioactive material. And he fired it at a sheet of gold. And most of the time, these alpha particles, they will go right through the gold sheet, right? So this is like a gold foil, just like a...
So the particle can just pass straight through then?
Yeah, they can travel straight through. That is actually the not the surprising bit. This gold sheet is made of these atoms, and they're probably arranged in a way where there's gaps for the particles to cut right through. Now, what's really surprising with this experiment is that occasionally, when they fire these particles at the gold sheet, the alpha particle that they fired, actually did sometimes 180-degree deflection, right? So these particles get deflected off the gold sheet and sometimes almost back to back.
At that time, did they not think the atom was made of anything then?
Indeed. In fact, at that time, the model of the small world, the atomic model, is that you have just these electrons dotted through this sort of membrane. I believe it's called the plum pudding model. So there, at that time, there was no evidence of something like a proton or even a center. When they detected some occasional times where the alpha particles get deflected, they drew up two conclusions. One, that the atoms are mostly empty space, right? Because these alpha particles just pass through them. But two, whilst it's mostly empty space, there are these centers in the atoms where it's positively charged. So what lesson we can draw from this experiment is that when you fire something very fast at your target, when you talk about small scales, this is a means to what we call probe the target or to study the target. Because the real sort of gold nugget of discovery from this experiment is that there was this deflection, right? So when the alpha particle comes into the gold foil, it bounces away. And this bouncing gave us a clue of what the inside of the atom is. If we take this lesson and then pump up the energy scale, so if we make our source faster, so if we choose something like the alpha particle, but for it to move faster, we can probe a deeper structure. So at the level of Rutherford, he managed to probe the atomic structure. So he managed to discover something about the center of these atoms. So that's called a nucleus.
Did they have any understanding of what a nucleus might be made of?
No. At that time, there was no real evidence of what the atomic structure should look like. And so he set up this experiment to find out. And so now, if we want to talk about quarks, which are on a even smaller scale, they're buried deep inside this proton. And we can actually discuss that a bit more afterwards. But the idea is, if you want to study them, you have to fire something and collide with these protons at such a violent process where it can actually start interacting. If you think, as an analogy of the alpha particle and the gold nucleus, you want to fire something to actually bounce off.
A bit like a bat with sonar.
Yeah, we want to send some kind of signal or a particle towards the proton. And if the signal is strong enough, i.e., if the particle is energetic enough, it will probe the structure of the protons. So we've been using this very simple idea since the early 20th century, but the means to do it has become more and more sophisticated over the decades. And today, of course, we have these experiments actually constitute the largest man-made machine in the world. The current largest experiment is done in Geneva at CERN.
Is CERN the same thing as the Hadron Collider?
That's right. So this is the machine is called the Large Hadron Collider. So instead of using alpha particles to bump them into the Go atom, we now use two beams, two collections of protons, and we spin them around the rings and collide them together so that we can study the internal structure of the protons.
Is it just a massive version of the bouncing particles off the sheet of gold experiment?
Yeah, well, if we have 5 hours or something, we can really try to do it justice. Of course, today in 2020, we're not just smashing protons together to know what's inside the protons. The alpha particles from the 20th century today are the protons, but they themselves are also the target. By smashing these protons together at very high energy, we can think back on this very famous short equation that Albert Einstein came up with, E equals mc squared. All this energy can be converted into mass, and it can help us to discover new particles. And that certainly made sensational news in 2012 when these protons that crashed into each other at really high energy produced something that theorists have suspected. They called the Higgs Boson back in 2012. But that may be a story for another podcast, I think.
Do you know if the Higgs boson is another type of quark, or is it something completely different?
Yeah, so it's more of the latter. So it's unlike the quark in the sense it's not part of the same family, if you will. They belong to a different, if you will, species of particles that we call gauge bosons.
Sorry to ask another question that might not be in your field, but was there any truth to the idea that the experiments in the Large Hadron Collider could cause black holes to form?
Yeah, I'm glad you brought that up, because I'm sure everyone is thinking about it when they hear that the podcast is transitioning to the LHC. So at first I thought it was bogus before I got to the university. And then in my third year, so I took a particle physics course, and the people who lecture, more often than not, are somewhat associated with the Large Hadron Collider. And so it turns out that this concern was, in some sense, it was real. In any big project, one has to assess all the possible risks, and there were concerns, and that's all they were. There were just these concerns that when we produce so much energy in this small amount of space, when these protons come and collide together at such a high energy, they were wondering whether we might produce a really mini black hole. And the follow-up question is, if we do produce it, does it become stable? It's okay if you produce it and it evaporates away, and if it disappears. But if it becomes stable, it's going to start eating its surrounding, right? I guess that's the sensational concept that we all have when we think about black holes at CERN. I'm telling this story because there's a very good lesson of ingenuity that comes with it. It's a valid question. While I believe most people thought it's really unlikely that's going to happen, but they wanted to set out to prove it. And they actually did something I find really ingenious. They just looked to the skies. So every moment right now, you and I, Jack, we are being bombarded by what we call cosmic rays. So they're just particles that's been streaming through space, and when they pass through our atmosphere, they interact with the ozone or something. And some of them will continue to stream right through them and then through us as well. So some of these physicists, they could measure the amount of energy that these cosmic rays interact with the ozone. And they find that it's actually much higher than the energy that's being produced in the Large Hadron Collider. So what this means is that the collision course between these cosmic ray particles and our ozone particles is at an energy level that is much higher than that in the Large Hadron Collider. And if we're not observing, mini black holes being produced in the sky, we shouldn't be worried about it being produced in our experiments. So, in that sense, that's a very resourceful, very out of the box way of thinking about this problem. Like they look elsewhere for the answer. I should reinstate that whilst I called it a concern, it wasn't as though, we have to halt this project because this could be a global catastrophe. It was never elevated to that state, I believe.
Yeah. So we went off on a bit of a tangent there, but returning back to your own work, you were going to explain a bit about what the different groups of quarks did.
So these quarks, as I said earlier, the protons are made of two of these up quarks and one of these down quarks. And the neutron is made of two down quarks and one up quark. At the very beginning of this podcast, we mentioned this particle zoo. The protons and neutrons have a multitude of cousins. The up and the down, but also a variety of other these flavors as well, the strange, the charm, the top and the bottom. So in the experiments, we only actually see the protons and the neutrons. I'm using the word see in a very loose sense. So we see the protons, neutrons, and their cousins. What we don't actually see are the quarks themselves. So it's not as if, if I crash these two protons together at very high speeds, one single up quark is going to spit out, and then we're going to observe it in our detector. This actually never happens. That's one of the peculiar things about quarks. The sort of one-liner that we can unpack is that quarks are never observed on their own in the world we live in.
So they're really solidly stuck together then?
Yeah, so they always come in either pairs or triplets. Like three of these quarks, as I said earlier, make the protons and the neutrons. Two of them can also make some other particles as well, but they never appear as one up quark whizzing about in the air. This was something that there was no reason to suspect that this should happen. So we think of quarks today as one of the most fundamental building blocks of the universe, alongside with the very familiar electron. Now we can see the electron as in it exists on its own. It doesn't need to sit together in pairs. It doesn't need to travel in pairs. So the electron is one of the building blocks of the natural world, and so is the quark. And yet the quarks, they don't exist on their own. They always exist in pairs and triplets. So that is something that I find very interesting. It also creates a massive headache in research in fundamental physics. These headaches spawn jobs, right? They spawn research topics. They allow people like me to do research. So maybe I'll unpack that a little bit. Because you can't study the quarks on themselves. You always end up studying the protons or the neutrons or their cousins. Because we only ever see in the experiments the protons and the neutrons and not the quarks themselves. We need to find another way to study the quarks, if you will, like individually. For example, if I wanted to ask the question, how does the behavior of the quarks influence the behavior of the protons? So how does the smaller constituents, how is it that when we change the smaller constituents, will we change the thing that they make up?
How would you experimentally figure out what one change to one quark would do to the others then?
Well, that would be an interesting question to ask about regarding these quarks. And so to do that, we have to actually run simulations. So if we simulate quarks with slightly different properties, we can produce a particle, let's say the proton, with a slightly different property. Do you see what I mean?
Yeah, so you really have to rely on computer modeling over...
That's right, because quarks cannot be seen in nature, in the real world. We have to simulate them on really massive computers to try and reproduce the results that we see in nature. So things like the protons and the properties of the proton, It's not that the Large Hadron Collider is not powerful enough to probe the quarks on their own, to study the quarks on their own, but it's a matter of just the way nature is today in 2020, that we have to simulate them. I guess I want to drive this point home. It's not that we don't have a powerful enough microscope to stare at them. Like they are completely censored from the rest of the world. So they exist, if you will, behind the shell of the proton. Although, we should take that statement with a grain of salt, in the sense that what we only observe in experiments are the protons and the neutrons and such.
Yeah, it wouldn't be possible to dig that far down into an atom. So now that you've given quite an extensive background to your field, what is the aim of the research that you're doing or is going on in your group at the moment?
Well, we'll go from the big picture downwards. The way that fundamental physics works today is that we're built on the foundations of the previous discoveries and the previous works, and we have this thing called the standard model of particle physics. So it's, if you will, it's like a family picture, all the different building blocks that make up the physical universe. We know that it describes the universe very accurately. All these tests that we've been doing from the 50s all the way to 2020 have shown that this family picture is very accurate. But it's also incomplete, because we give it such a noble name, the standard model of particle physics, right? It's almost suggesting it should be able to account for all physical phenomena. And for the ones it does account for, it does so amazingly, like precisely. It really precisely describes the world that we see around us. But there are a lot of things that the standard model, as we know today, that does not describe, or rather it has nothing to say about certain phenomena that we see in the world today. If this is supposed to be some kind of like a master theory that can describe the world from the bottom up, it's clearly not complete yet, because there are a lot of other phenomena that it can't describe. So honing in a little bit more, the standard procedure in research is to look at what the experiments measure, because that's the real world. The experiments give you a number, and then you try to get a prediction from the model. So that's the one that the theorists come up with. They try and get a prediction for the model, and then they compare the prediction to the experiment. If the experiment's number is different from the model, it means that the model is incomplete, right? And maybe it can suggest ways in which the model can improve itself. So this is how we sort of make progress in particle physics. This sort of like joint work between experiments and theory. So there are certain things that the model cannot predict. One of the reasons being, we can't see the quarks on themselves. So we need to get numbers from simulations as well. So in this big push to find out the limits of the standard model, as in where does it stop short, we try to provide these simulated results that we can also compare with the experimental results. So in this sense, that's where these kind of PhDs are heading to. You try to develop the computational tools, the sort of conceptual understanding, of what you want to compare in terms of or what quantities you want to compare with the experiments, and then you work hard to get this simulated quantity.
Yeah, I think often people think the goal is to replace old theories instead of update them and change them and make them more accurate.
That's right. There were times in history where an old idea really had to just go. But with many of these major peelings, shedding of these old ideas, we come to something that becomes increasingly robust, but still incomplete. So this is something the standard model of the particle physics is an example of. It's built on a lot of big corrections in the previous century. But today, obviously, it's not the full picture. we continue to try and find ways to extend it. It's not to say that it's wrong, because the things that it does describe, it describes really well. It's just not telling the full story. So we're trying to piece together missing jigsaw puzzles on the edge of this picture to try and build a bigger canvas out of it.
And I'm guessing when you're working on this, a lot of your day-to-day work is coding.
Yeah, that's right. In this particular field, when we study quarks via simulations, it's a bit of a juggling act where you got to know the physics well. So you got to know what properties you want to study about the quarks, and then you got to have the programming knowledge as well to make it possible to get the numerical answer out.
Yeah, so quite a varied skill set that you need then. Now, as my last question, if you could go into a different field of physics or other sciences, is there anything else that you'd be interested in researching or finding out more about?
Yeah, well, the short answer is yes, because it's going to sound quite silly, but it's pretty interesting kind of research. Even when I say my field of research is in particle physics, today particle physics is it branches off into so many little subgroups, sub branches of research. Everyone's focusing on a very small detail that somehow probably relates back to the standard model of particle physics. So when I was applying for PhDs, one of the challenges was to decide which of these sub branches do I want to go into. So in the end, I've decided to study these quarks, but there is definitely this other, not completely unrelated, but this other branch where it's motivated by the following question of why is there more matter than antimatter? So the model that we've come up with was that nature should have produced equal amounts of matter and antimatter, or put it another way, there should be no preference between one or another. This is something that clearly is something the standard model says, but it's not being reflected in the real world, because these things we call antimatter, let's say like the antiproton or the anti-electron. So what they are is that they are the exact same particles as the normal matter, but they have the opposite electric charge. So if an electron has an electric charge of -1, the antiparticle, which we call the positron, that's going to give the game away, but the positron's electric charge would be a +1. You see that they are almost identical, the electrons and the positrons, but their electric charges are the opposite. What happens is that when you have matter and antimatter coming close together, the term we use is they can annihilate each other. When these matter and antimatter come in contact with each other, get reduced into just pure energy or light. So you can imagine that it would be pretty hard to produce a universe with planets and stars if there were equal matter and antimatter. So something has happened in the very early times of the universe, and it was measured actually. Like an experiment was done looking out far into space, and they find that in the earliest few seconds after the Big Bang, when you have for every 1 billion antimatter particle, there was a 1,000,000,001, just normal matter. Yeah, so something happened very, very early on, seconds after the Big Bang, where the matter and antimatter, they annihilate each other, leaving behind a trace amount of matter that goes on to form this rich universe we see today with stars and planets, people like you and I. So this mystery, I really like it because it's easy to understand, like compared to, trying to explain about quarks. It's easy to understand because we experience it every day, but it remains, one of these very ground-shaking questions in particle physics. That's another example that the standard model does not really say much about, and it was something that I was really hoping to get into as well.
That brings us to the end of this podcast episode. Thank you for coming on to talk about your subject. For anyone who wants to hear more from the Sci-Fi podcast, we'll be posting a new episode each week until the end of this series, and you can also follow us for updates on Twitter and Facebook by searching for Sci-Fi podcast.